Yeah, the discussion of simulation that's been going on here may leave you a little bit mystified, wondering exactly what are we talking about here. Many of you, since you're producing products that are maybe structurally complex, have encountered the notion of simulating by using, say, finite element models or something like that to calculate the stresses in a part, or perhaps aerodynamics if you're in racing. In this case, what we're going to talk about is vehicle dynamic simulation. That is, being able to simulate how a vehicle rides and handles, so to speak. So it has been presented to you as a technology that contributes to dealing with the electronic stability control certification issue here among the SEMA members. And it is one of the ways to replace really the costly testing of multiple vehicle variants. So we're going to just take a brief look at what simulation can be used for, or how it's used for with electronic stability control, but also kind of hopefully introduce you to other applications that you may find to be of interest. Let's see if we can get the mouse awake again here. First of all, what do we mean by vehicle dynamic simulation? This is the virtual vehicle. When we've talked about the virtual world so many times, it is literally the same thing replicated on a computer that you would normally do in the physical world. So if you want to actually simulate a vehicle, you have to, first of all, have some information about the vehicle itself. So in the simulation world, that's just a lot of numbers that characterize a vehicle. Now, in our case, with producing software like this that's used by various people, we end up giving them a lot of generic vehicles to start from, because this is always the tough part. But first you have to describe the vehicle by a set of data. Then you have to have a plan for some sort of a maneuver you want it to go through, shown here as a control input. Basically, what tests do you want to do? If it's a brake issue, you're going to do tests of various kinds of braking maneuvers, whether it's a stopping distance test or something else. And then in addition to that, you need a place to do it. So everybody who goes out and tries to do a test has to find an appropriate test site location. So we have these kinds of elements that are shown here on the left. This is what simulation is doing in the virtual world. It has a virtual vehicle, it has a virtual test procedure, and a virtual place to run the test. Whether it's a proving grounds or the skid pad on a proving grounds, or running on up and down hills, whatever it might be. Once you have all this information together, as shown here on the left side, the next thing is to simply go ahead and run the test. In the virtual world, that's fairly easy. That's really just running the math model that is shown here. In the middle, you click on it and the math model runs, and it produces one of two kinds of output. One is an animation type of output, where the animation could be, it's basically simply showing the specific actions of the vehicle in the course of the proposed or planned maneuver that you did. In this case, I'm showing an animation of one of the rollover tests that is has been required by our National Highway Traffic Safety Administration. This is called a, this animation is a, excuse me, let me get it back there a second. It is a fishhook test in which a severe steer is put into the vehicle, and the vehicle ends up steering first in one direction than the other. The steer rate is like 2 revolutions per second. It's a very severe maneuver. And in this case, what I've done is really just set up 3 vehicles, one of which is unsuccessful. That's the red one. The yellow one is successful, and the one in between, of course, is one that has to rely on the outriggers to keep from rolling over. But this is a very important type of test that has been done by OEM manufacturers here in recent times. The other thing is that the simulation also puts out a list of data here that is then able to be plotted for you. For engineers, we like to look at numbers. Plots are one way to do it. There's kind of an interesting aspect about testing in the virtual world, and that is that the vehicle is fully instrumented. If you want to do a test, let's say with a new suspension component, you might want to know what the loads are going to be, say, in a spring hanger bracket. And for those of us who come from industry, we know the effort and expense of building a transducer to measure it. Guess what? In the simulation world, the 400 or so variables that are computed here in this virtual world are there for you to observe. You can go look at exactly what those forces were, and after the test, you can go back and dig out all of those different parameters as you come and try to understand exactly how this system works. You've seen it here being mentioned with respect to the electronic stability control testing that is required by the Federal Motor Vehicle Safety Standard 126, which is also, by the way, duplicated in outside of the United States in the ECE regulations. 13H is effectively the same test. The certification process is a little bit different. In the United States, it is a self-certification. In Europe and around the rest of the world, you normally have to demonstrate to a government agency that you have been able to certify it. It is the test in which the steering wheel is simply put through sort of a sine wave maneuver. It steers first in one direction and then the other direction, and when it gets to the extreme of the steer, it's held for 1/2 second, and it's returned to a zero steer position, and the vehicle itself has to be able to stay stable. Actually, this is one of the SEMA tests here, I believe, that has been conducted by my colleagues. This is the simulated version of this pickup truck going through one of these steer maneuvers. Now, there are, as you saw, many steer maneuvers, starting with fairly low angle steers going up to very severe levels where the vehicle attempts to roll over. So this is that thing called the electronic stability control test. But at the same time, it seems worthwhile to point out to you that this is just one place where simulation is helpful to you. It is trying to deal with a complex world where when you take a vehicle and you modify it in any way, you have to ask yourself the question, is the performance in this regulated government test going to change? Here are some of the principal vehicle components that affect electronic stability control performance. So if you make or sell any one of these, you need to think about what that really means with regard to altering a vehicle after it's been produced. Actually, this presentation by Scott Dahl, he indicated there could be as many as, say, 400 different variables that will affect the performance in electronic stability sine with dwell test. So there are a lot of things for you to think about. But it can be used lots of other ways. The issue really looking at the fact that cars are extremely complex in these times. I have shown here a car that has a number of control systems associated with electronic power steering or electronic power assist or lane keeping assist, or some of you may be familiar with some of the trailer yaw control things that are being done now with pickup trucks. Of course, there are anti-lock brake systems, and down here on the right, the other dynamic brake proportioning systems, tire pressure warning monitoring systems, electronic stability control. I have all of these shown. It goes on and on. In the middle, I've added one more. This thing that's shown as advanced driver assist systems. This is a lot of these other things that were being mentioned by John. The things that are coming down the pike. Our cars are really sophisticated today. If you have a new car, you know what I'm talking about, the amount of controls that are on there that will potentially be influenced by any change in the vehicle. But you can use it for many things. For example, many of you get into performance, just plain old acceleration performance. This is a place where simulation can help you with basically the engine tuning, checking and picking gear ratios or shift points, figure out top speeds, look at fuel consumption and emissions, the aerodynamic effects on performance, differential controls and locks, tire traction and stuff. Here's an example of a simulated drag race. This was, oops, it is giving me a little difficulty here. This is a simulated drag race between the Camaro and a Mustang that we did some time ago here for Motor Trend magazine, when they had the Mustang performance data, but the Camaro, they couldn't thrash it, so they said that could we simply simulate and calculate how fast the Camaro could pull off a quarter-mile drag, and this is the data. Of course, I have to tell you that a lot of the data came from General Motors, so there could be a little bit of a bias as to who would win this race. But if you want to look at acceleration performance, this is a big deal. Another is looking at braking performance. Everyone gets involved with that as soon as you start trying to change a wheel or a brake or anything like that. And it will affect the stability, the stopping distance behavior. Here's a simulation of two vehicles. Actually, I believe this one shows the one car, blue car with an anti-lock brake controller. The red car was a uncontrolled vehicle, and they're stopping on a split an ice and a dry road surface. And you can see how easy it is to really figure out how will this affect the behavior of the car. Actually, in this case, being able to see the advantage of having anti-lock brake controllers on it. Also, the ability to go ahead and overlap two vehicles. That's always kind of a handy thing because you get a very clear picture of A-B comparisons. Anything you do, you change the center of gravity height, you put big wheels on. Big wheels will diminish the effective brake force that you get at the ground, and so you will have increased stopping distances unless you can arbitrarily increase brake pressure delivery. So there are lots of questions that can be addressed using simulation. Ride simulation, this is always kind of interest. Here is actually the lifted truck running over a series of sine wave bumps. In this case, all you get is sort of a visual picture, but I think you might be able to identify a little bit with what that truck feels like when it goes over those bumps, because some of you have been in trucks that have had lift kits put on them, and you get more of a fore-aft pitch behavior out of the truck as you elevate the truck above the ground. So we have these kinds of lessons that can be learned with regard to just simple ride behavior of a vehicle. Handling is another key area where we're interested in being able to quantify the behavior of the vehicle. This actually is showing a baseline truck with a lift truck going through a slalom course. And you could see, in this case, a little bit of a difference between their performance. But actually, at the end, when the brakes come on, notice one thing. The blue truck has bigger wheels. So it takes longer distance to stop, the kind of detail I was mentioning to you a few moments ago. Another case is kind of an interesting one. This is a rather old example, but one that you might find interesting in that we a lot of times want to look at how any change to a vehicle will affect its ability to get around, say, a race course. In this example, what we're looking at is some work that was done with Ricardo, and it's not a great animation anymore, but it shows 3 vehicles running around a race course, and the only change here was the cam profiles. The only thing it could sort of change from race to race quickly was throw another cam in that same engine, not change the engine. And so the whole exercise centered around finding out which cam profile gave the best time, the shortest time around that track. And you could see that different performance curves for the engine caused or allowed one vehicle to nudge ahead of the other, etc. But the thing that really mattered is what was the order of finish when you get to the end of the race course, or the end of the lap. Other little nuances of places where you can use simulation. I've just thrown a couple more in here. For example, trailer towing is always potential interest to you. This one is actually 2 trucks with a trailer, one of which has a yaw control. And you'll notice that the simulation world allows us to sort out exactly how they will behave and how that will impact on the ability and the value you can provide to a customer. Off-road mobility, oh yeah, it's another one that's always of interest to most of us. We like to see vehicles going off-road. In this case, this is run as a 2-wheel drive, and it can't make the grade until it kicks into 4-wheel drive and then goes ahead and finishes and makes its way up the road course. And then finally, just to show sort of what you can accomplish in simulation, this is a complex maneuver that we can do easily in the simulation world. Oops, that goes away too quickly. We can do it in the simulation world. This is the bootleg turn, or various names for it, where you back up, turn the wheel, hit the brakes, spin around, and then drive away. And this is something that is easily accomplished in simulation. We do it with trucks even. If they tip over, you don't scrape the side of the truck. You just go back and set it back up again, and you can replicate that maneuver again. Well, there's a lot of opportunity for those of you who think about getting into the virtual world for designing your products by using some of the simulation tools available. I think if anything, the one lesson, though, that we would try to bring to you here at SEMA is that this is a place where cooperation between different people and different organizations can save you effort and money. And what SEMA is really trying to do here is take this fairly sophisticated tool and make it available to you. You can do your own simulations, but at the same time, the words you're hearing at this venue is that it's to your advantage to be part of a group that is trying to build up data sets and capabilities to use these tools to help you develop better products for your customers. Okay.